now.
All right, thank you everyone for coming back on this second week of the course in Quantum Systems Information and Entanglement. Today, I will talk about teleportation and entanglement. Last week, we introduced the basic principles of quantum systems, and today we'll put into practice the things that we learned last week. We'll talk about the property of entanglement, try to interpret it and see how it's useful for the teleportation. And next week, we will get into the concept of decoherence and see how noise affects quantum systems, how quantum systems can be represented in that case, and also how we can deal with those problems in order to construct useful applications in platforms like quantum networks. Today, I will start off by discussing about quantum gates, both for single and 2 qubits. Then I will use those gates and knowledge from previous lecture in order to introduce quantum teleportation. I will go step by step on this protocol, and I will conclude this lecture by discussing entanglement interpretation of it and some misconception about entanglement and its resource nature. All right. Last week, we saw that a 2-dimensional quantum system, a qubit, can be used in order to encode information on it. And we also discussed that we can decode information, we can extract information from a qubit using measurements, in particular projective measurements, for example, pi0 and pi1, which will collapse our states into the state 0 or 1, and with a specific probability, which depends on those coefficients, those complex numbers A and B in the superposition of the qubit. Today, we'll go a step further and talk about quantum gates, which are nothing but quantum evolutions. You will see in a few seconds why we pick the name gates instead of calling them just quantum evolution. And I should also just remind that unitary transformations, which are all those quantum gates, satisfy this identity. We have seen already particular quantum evolution, which is represented by the Pauli matrix X, which in a previous lecture, we saw a specific example with some particular coefficients for the superposition. Here I take it in a more general form, and I have a general qubit, which evolves under this quantum gate, under this evolution. And as we can see, we have the swap of the coefficients B and A. I also represent here the Pauli matrix X in the Dirac notation. And if we pay attention on what exactly is happening for the specific 0 and 1 states, we will see that this gate takes the state 0 and gives us as an outcome the state 1, and vice versa. And that, of course, resembles the NOT gate in classical information processing, which takes the bit 0 and gives us 1 and vice versa. And that is why sometimes in the context of quantum information, we call the Pauli gate X as the NOT gate for quantum systems. Of course, the NOT gate is not the only one that is useful for quantum applications. There are a lot of different gates. Here, I will just show you 5 of them, which are particularly interesting and simple to describe. We also have the gate Y, which is the Pauli matrix Y, and third Pauli matrix Z, which we saw on our previous lecture. We also have the Hadamard gate, which is really important because, as you can see, it takes the state 0 and creates a superposition of 0 and 1 with a plus sign, and takes a state 1 and creates a superposition of 0 and 1 with a minus sign. This is interesting because those gates can be used in order to induce coherence in a quantum state. And the Hadamard gate is, as you can see, a combination of the Pauli matrices and a special case of the discrete Fourier transform. So it's a rather important gate in general. We can also have the phase shift gate, which is the gate that, if you remember, we saw on the very first slide of our previous lecture when we were discussing the Mach-Zehnder interferometer. Of course, we can have gate for more than one qubit. So that's why let me first start off by giving some context on how we can mathematically represent systems which contain more than one quantum state. Let us assume that we have two quantum states, psi1 and psi2, which now I present them both in the conventional notation of vectors and in the Dirac notation. And to familiarize ourselves, I color-coded the elements so you can see exactly what is happening. And given those two vectors, if we want to create a global quantum state that incorporates both of them, we can do that. This composite system can be represented with this capital Psi, and this operation, which is called the tensor product. Sometimes it is also called the Kronecker product for low dimensional systems in linear algebra. Those two things coincide, so I will keep using the term tensor product. And this operation acts in the following way. We take the first coefficient, the first element of the first vector, and multiply it by the second vector. And then we also take the second element of the first vector and multiply it with a second vector. So the outcome will be another vector, but the big difference now is that it's a four-dimensional one. So a tensor product takes two-dimensional vectors in this case and produces as a result a larger dimension and a four-dimensional vector. I also want to show you how this is represented in the Dirac notation, because I will be focusing in this notation throughout my lectures. So in this Dirac notation, we have those two vectors multiplied with the tensor product. And if we expand this, we get this kind of long expression. And in order to have a more concise notation, sometimes in this Dirac notation, what we do is that we suppress this tensor product symbol within the ket. So as you can see, the multiplication 0, tensor product 0 becomes just a ket, which has two zeros in it, and so on. I just wanted to let you know about it, because when I will be doing some calculations, I might be using the this concise notation of the tensor product. All right, so having that in mind, we can proceed into seeing what is happening with two qubit gates. But before, let's also remind ourselves that the analogous case in classical information are the 2-bit gates. For example, here I have the AND gate, which takes 2 bits and gives 0 whenever we have 0, 0, 0, 1, or 1, 0. Otherwise, it gives 1 when both of the input bits are equal to 1. And in an analogous way, we can create 2 qubit gates. And here I will present to you one of the most important ones, the so-called control NOT gate. All right, so control NOT gate is represented by this dot, which is the control qubits, and this the below sign this target, which is the NOT operation, which the NOT operation is performed only if the first qubit is in the state 1. So in this case, when we have for the first qubit the qubit 0 as a control, then the second qubit remains the same. So the state 0, 0 has as an output the state 0, 0, so nothing happened. For the case when we have as an input 0 and 1, then the output is 0 and 1. However, when the first qubit is in the state 1, then the NOT gate is applied on the second qubit. So the state 1, 0 has as an output 1, 1, and analogously 1, 1 gives as an output the state 1, 0. A first big difference, as you can see, between classical and quantum gates is that in quantum gates, we have two outputs, while in the classical gates, we can have a single output. Let me also show you how the C-node gate is represented in the Dirac notation. We just have the C-node operation applied on the state psi. In general, a state psi, which is a two-dimensional state, a state in a two-qubit state, can be represented with this vector with coefficients A, B, C, and D in this basis, and this will be the output. Let's color code to see exactly what is happening. The first vector and the second remain the same, so the only difference is on the third and the fourth, which, as you can see, they have been swapped because the first qubit was equal to 1, so that was the control, and then we applied on the NOT gate only on the second one. I know that it's really hard to keep track of all those zeros and ones, and it's not easy to do calculations in those presentations through slides. However, don't worry about it, because whenever I will be using any quantum gate, I will always give exactly what is the definition of the gate and what is happening with those zeros and those ones, so you don't have to remember anything. All right, so that was all regarding the introduction on quantum gates. Let me now proceed on quantum teleportation. Schematically, first of all, let's describe what is a teleportation as a protocol in general. So the idea is that we have an input state, an input quantum state in one laboratory A, that we can call it Alice. So Alice has a state, and she wants to transmit this state into another laboratory, to Bob, let's say, but she's not allowed, she doesn't want to just send it through a optical fiber or through free space links. She wants to make Bob get the same state without a direct transmission. And that is actually possible with this protocol, which requires that Alice and Bob pre-share a state that we call resource, because as you will see, it's really important and acts as a resource for this operation. I have two arrows, and that means that this is a 2-qubit state in our case, and 1 qubit goes to Alice and another qubit goes to Bob. Then Alice applies certain quantum gates, so she put her state and one part of the resource state in coherence. She applies certain gates, she evolves this combined state, she applies certain measurements, so she measures the state and gets some classical information out of it, and she sends that information to Bob classically. So practically, in our case, she will send 2 bits of information, and Bob will get that information, which depend on the measurements that Alice applied, and he will apply certain quantum gates on his part of the resource state, and he will have as an output state, if everything went as planned, a state that is identical to the input state that Alice had. Now I want to make 2 important comments. First of all, this is not a quantum cloning operation. That's not a copying of a state, because at the time that Bob has an output state, Alice's state has been changed because she has already mixed it up with the resource state and through those quantum gates. So what is happening is that Alice's state is destroyed and Bob's state is in the same state that Alice's was before the protocol, and that's where the term teleportation comes from. The second point is that quantum teleportation does not occur faster than the speed of light. The reason why I'm mentioning that is that I've seen a lot of articles on the internet, on Twitter, people claiming, overhyping quantum teleportation. Quantum teleportation depends on classical communication of the measurements that Alice applied and received through this combination of the input and resource state. So quantum teleportation cannot occur any faster than the speed of light or instantaneously. We have to abide by this principle, the basic principle of physics. Also, I want to mention that this protocol was introduced back in 1993 by Charles Bennett et al. And even though this is probably a nice key schematic to represent quantum teleportation, if we want to actually do calculations and see what exactly is happening, probably we have to represent the same protocol in a different way, in a chronological way, if you will. So this is the circuit of teleportation, and we go chronologically from left to right. And here as psi, this is the input state. And if everything goes as planned, we will have the output state be the exact same one. This here is the resource state, which I have a detailed explanation of how we actually can construct it. We have two states in two zero states, and then we apply two gates, the Hadamard and the C-node gate. This is the resource state. Those are the quantum gates that belong to Alice. All those things are happening to Alice's laboratory and those measurements. And then we have the dashed lines, which correspond to the classical communication from Alice to Bob. And finally, the quantum gates that Bob applies on his state. So you can imagine this circuit as such that the first two lines, the first two qubits belong to Alice, and the third one belongs to Bob. All right, so have that in mind. Let's be more specific and try to teleport an arbitrary state in this superposition, which brings me to another point. The point of teleportation is to teleport a state that Alice and Bob don't know in advance, particularly Alice, because if Alice already knew what was that state, she wouldn't have to go through this these tasks. She could just call Bob and tell him what exactly are the coefficients A and B. So the teleportation makes sense only when Alice has no idea what the state is, Bob has no idea, but they are able to transfer it from one point to another. All right, so in our case here, we have the global state size 0 as the tensor product. It's a combination of 3 qubits. The first qubit, which is the unknown one, and 2 more, which start in the state 0. And I also color-coded them, so we're on the same page. We know exactly what's happening. And then we substitute the state psi, which is this arbitrary qubit. And then let's suppress this notation and make it more concise. And we have now these outputs. It's not an output state, it's a global state before the protocol begins. All right, so let's move to the first step, which that's the global state psi 1. And as we can see, we apply Hadamard gate on the second qubit. The definition of the Hadamard gate is given at the bottom of the slide. And then if we substitute the state psi 0, we have that expression. And then applying the Hadamard gate, we get this state, which of course is the state that we apply the Hadamard gate on the second qubit. So 0 becomes this superposition of 0 and 1 with a plus sign. And the state, the other state 0 also creates this superposition. So in total, we have this state. As you can see, those are simple calculations, simple linear algebra. I know that sometimes might be hard to follow exactly what is happening, but I always, when I go to the next step, I always remind ourselves what was the state that we found on the previous one. So moving to the second step, we have to apply now the C-node gate on the second and third qubit. And below on left, on the bottom, we have the definition of a C-node gate for those vectors. And this is just a substitution of the state that we found on the previous step. Now, applying the C-node gates, we end up with this state because the state 0, 0 remained the same. The state 1, 0 changed to 1, 1 because the first qubit was 1, meaning that we have to apply a NOT gate to the second one, so 0 became 1. The state 0, 0 remained the same, and the state 1, 0 changed to 1, 1, similar to the other one. Let's move on to the third step. On the third step, we apply a C-node gate on the first 2 qubits, substituting side 2 from the previous step. We have that expression, and then applying the C-node on that vector, on that state, we end up with these states. And again, let's go step by step and see that the state 0, 0 remain the same. Similarly, 0, 1 remains the same. 1, 0 changes to 1, 1, and 1, 1 changes to 1, 0. Moving on, we have the last operation at Alice's laboratory, which is again another Hadamard, but now it's a Hadamard operation on the first qubit. Substituting from the previous one, we have that state, and applying the Hadamard operation, we see that we create some coherences for the first qubit. However, those are just vectors, and if we do some rearrangements on this expression, we will end up with this vector. So what I did here is that I tried to drag all the coherences, all those superpositions on the third qubit that belongs to Bob's side, and left the state 0, 0, 0, 1, 1, 0, and 1, 1 at Alice's side. Next, we have the step where Alice performs certain measurements on her first 2 qubits, on her qubits, and this was the state that we found in the previous step. And now, if we focus a little bit on the measurements that Alice performs, we see that we have this outer product of N and M. That implies that Alice measures either the state 0 or the state 1 for the first qubit, and she also measures either the state 0 or the state 1 for the second qubit, which means that there are 4 possibilities. This possibility, second, third, and fourth, which now I represent as those observables that we saw last week. As you can see, I also introduced an observable, which is the identity. Practically, this is just for consistency reasons, mathematical reasons, because we don't do anything on the third qubit. We only apply those measurements on the first 2 qubits. So you can imagine as an observable for the first 2 tensor product identity, meaning nothing happens on the third. And those 4 observables, those 4 measurements occur with the same probability, 1/4 each. So if you remember on our previous lecture, we discussed how we can represent a quantum state after it has been measured. So now what is happening is that we have a global state, psi phi, and there are 4 possibilities depending on what happened to the measurements that Alice's did. So if Alice had measured the 0 and 0, that would imply that we get this state. And this is, again, a global state for the whole, both Alice and Bob. And since we have now this tensor product, 0, 0 tensor product, the rest of the state, we can just ignore the first 2 qubits, because from now on, we move to the second laboratory, the Bob's laboratory. So we only care about the third qubit. Analogously, when Alice measures 0 and 1, the global state is given as such, and we only care about this state, which is colored as blue, which is the state at Bob's side. And obviously, we can have 2 other states for the cases when Alice measured 1, 0 or 1, 1. Which brings us to the last step of teleportation, where Bob has a state, this state psi ij. He has no idea what is the state, but he does know after classical communication what was those coefficients n and m. What was if Alice measured 0 and 1 on the first or the second qubit. And based on this classical information that Bob gets, he applies his quantum gates, which are the Pauli gates x and z, to the power of m and n. So those gates depend directly on the measurements that Alice had. For the case where Alice communicates with him and tells him that she measured 0 and 0 for the first 2 qubits, then he has to apply practically nothing because it's x to the power of 0 and z to the power of 0. He got lucky because in that case, the state that he received was actually already in the input state of Alice. However, this is just one of the 4 possibilities. If he gets 2 bits of information and one is 0 and the other is 1, it means that he has to apply the X gate to the state that he had after the measurement, the state psi 0, 1. And then applying this X gate to this state, practically he gets back to the input state of Alice. So that's, again, successful. And analogously, if he had measured 1, 0, he had to apply the Z gate on the state psi 1, 0, which will end up with this operation. And again, he finds the same states. And last case is when he receives the bits 1, 1, meaning that he has to apply both of his gates, first the Z and then X. And again, if we do all the calculations, we will find out that the output state is always exactly what Alice had before the teleportation started. And let me also point out again that at that point that Bob retrieves this state psi, Alice's state is not anymore in the same state. So the state got teleported from Alice to Bob using classical and quantum information at the same time. All right, so that was all I had to say about quantum teleportation. And now I want to dive deep and see why teleportation works. What is the reason why teleportation works and why we cannot have classical teleportation in the same sense? And this is because of a particular property called entanglement. So we discussed about this state, which we call it the resource state for the teleportation. And we also seen how exactly we can create it. It's created applying a Hadamard and a C-node gate. Let's see exactly what this state looks like, because it seems really important to the teleportation. This state in the Dirac and the conventional notation looks like this. And for historical reasons, it is called the Bell state. Let us remind ourselves how we can represent composite states, because it is kind of obvious here that the Bell state is a state that corresponds to 2 qubits. And we already seen that if we have 2 qubits, psi 1 and psi 2, then we can create a combination of them through the tensor product, and we end up having this 4-dimensional vector. Bell state, as you can see, is 4-dimensional. So what we know for sure at this point is that if we have 2 vectors, 2 states, 2-dimensional ones, we can always create a composite state combining those 2 and having a 4-dimensional vector. The question is now, if I have an arbitrary 4-dimensional vector, can we always find 2 2-dimensional vectors that are equivalent to the first one if we apply the tensor product on them? And the answer to this question is no. In general, we cannot go the other way around. And a typical example of a state that cannot be written as the tensor product of two smaller dimensional vectors is actually the Bell state. So this is, as we see, an important, that there are states which have this particular property that is what we call entanglement. So more rigorously, for a composite state that cannot be written as a tensor product of two smaller quantum states, it's called an entangled state. Otherwise, this is called separable or a product state for this particular type of states. But okay, that is a mathematical definition. Let's see exactly what that means physically, what it means in practice. So in practice, entanglement means that entangled systems share a common property, but we don't know exactly which part has which share of this property before we measure it. To make it more clear, let's see an example with two electrons. So let's have a system of two particles, and we know that the property that they share is that the total sum of their spins is equal to 0. However, as you can imagine, there are two different cases that we can have this case. We can have two particles, and one particle is spin +1, meaning up, and the other down, or vice versa. So before the measurement, we don't know which particle has which spin, but we do know that in total, that system has a spin equal to 0. Mathematically, we can represent this state as the state phi. By the way, this is a variation of this Bell state that we discussed before for teleportation. And as we can see here, we represent with the vector 0 spin up, and with vector 1 the spin down. And it's kind of obvious at this point that there are certain correlations that are shared between the particles. You might have heard that entanglement is associated with correlations, and particular quantum correlations. And I also want to make a point here that in this representation of entanglement, when I define entanglement, there is no restriction about how far apart those particles can be. And that point is the reason why a lot of people sometimes misunderstand what entanglement is actually about, because the fact that two particles can be arbitrarily far away and still retain those correlations sometimes gives the impression that something weird is happening, something that one particle might affect the other in a weird way. So let me also make this comment, discuss a little bit more about what entanglement is definitely not. So entanglement, because you might have seen articles, tweets all around the internet about entanglement going faster than the light, the spooky action, of course, at the distance. There are a lot of different claims. Entanglement does not allow faster than the light communication. Nothing can travel faster than the light. Actually, entanglement does not even contain information. Entanglement contains correlations about information. So there is no cause and effect when we actually measuring one particle that affects the other, even though those two particles are perfectly correlated. In order to see exactly what's happening here, let us give an example of a classically correlated system that has a similar property and see why exactly the faster than light communication, this claim is unfounded. Let's take a simple example. Let's have a pair of gloves, and we have also two boxes, and somebody, let's say in the middle between Alice and Bob, without Alice and Bob knowing, he places those gloves on either box A or B, and they send those boxes to Alice and Bob can be arbitrarily far away. This means that there are only two cases. Either Alice will get the left-hand side and Bob the right-hand side, or vice versa. Alice and Bob know that they get one glove out of a pair. So whenever they open up their boxes, they know instantaneously what is the glove on the other side. And that, of course, does not imply that any information from a glove traveled instantaneously to the other side, from Alice to Bob, to change the state of the glove or anything. It just means that correlations exist arbitrarily of the distance, that because the correlations were created locally and two boxes were separated at a later point arbitrarily far away. Going back to the quantum case, if we have this quantum state, which is, as we said before, entangled, and we can associate it with spins up and down, we can send one part to Alice and the other part to Bob. And then there are two cases. The first case, which is associated to this superposition of the state. The first case is that Alice gets 0 and Bob gets 1. And the other case is that Alice gets 1 and Bob gets 0. So the spins are always perfectly correlated. I mean, in this case, sometimes I will use the term correlated for both perfectly correlated and anti-correlated. And of course, no information has traveled from one place to another, informed the spin to change direction or anything. Now, at this point, somebody might think that, okay, so what's the big deal about quantum correlations if we can do the exact same thing as we can do with classical correlations? Why is entanglement important in the first place? The important part of entanglement and quantum correlations is that even though in classical terms, a single property can be indeed perfectly correlated regardless of the distance, a quantum state can produce multiple properties which are simultaneously correlated perfectly. So we can have the exact same system, the exact same state sent to Alice and Bob, but if Alice and Bob decide to measure a different direction now for the exact same state, then the left and the right directions will be perfectly correlated. And similarly, if they decide to measure the orthogonal directions, meaning the inward and outward vectors here, again, they will find their states to be perfectly correlated. That might seem weird. Let's be more specific and see exactly why that is the case. So we said that this state is represented with this those kets, this superposition of kets with 0 and 1s. I also have them in the vector notation, but I also now, to be more specific, instead of calling them 0 and 1s, because sometimes this is too abstract, let's represent 0 with the up vector and 1 with a down vector. So in this case, we have the states represented with this superposition of up and down vectors. However, given that the Bell state is just a vector, it means that we can always find a different orthonormal basis to represent it. And a different orthonormal basis might be the one that is the spin has a direction of right or left. And if we use now this representation, this orthonormal basis, then the exact same state, the Bell states, can be represented as follows, with a superposition of left and right. And analogously, we can have the third orthonormal basis, which will be the vector pointing inwards or outwards. So the Bell states, the exact same state, Bell state, has this representation. So given that knowledge, if we go back to our example, we can see that if Alice and Bob decide to measure in the direction up or down, obviously those two things are perfectly correlated. If they decide to measure right or left, again, we have a superposition of perfectly correlated states. And if they decide to measure the spins that are pointing inwards or outwards, again, the quantum states are perfectly correlated. So in this sense, quantum correlations are stronger than classical correlations because in quantum systems, multiple properties can be simultaneously correlated and not just one. Somebody now can raise the question of, wait a second, if maybe we can do the exact same thing for classical states. After all, let us assume the case where we have a pair of globes and one is red and the other is blue. Then doing the exact same scenario, it means that Alice and Bob can end up with those cases, but here there is a big difference. The difference is that classical properties are compatible with each other, which means that they can be simultaneously measured. When Alice gets her glove, she knows at the same time that the glove is the left-hand side and also that the glove is red. And Bob knows that the glove is both blue and right-hand side, and vice versa, which means that practically one correlation reduces to the other. Measuring just the left-hand side, she already knows that the color of it. This is not the case for quantum correlations because quantum properties can be incompatible, meaning that measuring one property gives us no information about the other. And of course, that is the effect of the uncertainty principle, because in this case, I described three different properties, which are properties that are incompatible. They satisfy the uncertainty principle, meaning that when we decide to measure a spin on the up or down direction, whatever we end up measuring gives us no information about the state if we had measured it in a different direction. And of course, quantum correlations can exist in different ways. For example, previously I discussed about spins and those vectors. We can also have, for example, photonic states which are polarized. So then we will end up with, again, simultaneously three perfectly correlated properties which will correspond to the orthogonal, vertical and horizontal, diagonal, anti-diagonal, clockwise and anti-clockwise. And you can imagine that we can do that for any type of property, any type of quantum property in the same way. And let me also note how we can actually characterize entanglement. And we can do that with a particular mathematical tool, if you will, which is called the Schmidt decomposition. Schmidt decomposition means that every state can be written in that decomposition, meaning that it's those lambda coefficients are called Schmidt coefficients, and those EI and HI are orthonormal bases. And the number of the non-zero Schmidt coefficients identifies entanglement. Let's be more specific. If we end up having a case where having a state, we write it down in this decomposition and end up finding lambda 0 to be 1 and the other to be 0, then the state is separable. In other words, can be written as a product, as a tensor product of E0 and H0. And otherwise, if both coefficients are non-zero, we end up with this state, which is by construction entangled, which brings us to another point and a different interpretation of entanglement. We have already discussed during the first lecture about the concept of superposition. So the superposition is this idea where two states can exist simultaneously before the measurements. Based on the Schmidt decomposition and this characterization, that implies that entanglement is just the superposition of composite quantum systems. So when the system is not composite, it's called superposition. When the superposition is applied on a composite system, this property is called entanglement. So that is what entanglement is all about. Let's see two specific examples. The Bell state that we used for the teleportation was, of course, entangled because it was already written in a Smith decomposition. So those coefficients are equal to 1 over square root of 2. And another state, which is also kind of trivial, and again is already written in this decomposition, is this separable state. However, I don't want to give you the impression that characterizing entanglement is always trivial. For example, we might have this state that in order to see if it's entangled or not, it takes a bit more effort in order to write it down in this decomposition, and that can be done using a different now orthonormal basis. But since both coefficients are non-zero, this state is entangled. And this state, which even though it looks pretty similar to the previous one, is actually separable using this method to characterize entanglement. And given this knowledge on how to characterize entanglement and the fact that entanglement is definitely related to teleportation, let me conclude this lecture by the relationship between those two. So we're now back in the teleportation protocol, and we have as an input state. Here's just an example. So let's assume that we know what is the input state. This is the combination of 0 and 1. And the output state ideally should be the exact as the input state if everything goes as planned. And as the resource state now, we have this Smith decomposition, these quantum states, which is a superposition of the states 0, 0, and 1, 1. And there is this parameter x that varies from 0 to 1. When x is equal to 0, we have just a separable state. Otherwise, if x is anything but 0, the state is entangled. And in particular, when x goes from 0 to 1/2. And when x is equal to 1/2, we have this entangled state that we already seen, that it works perfectly. There's another question now on how exactly we can benchmark this protocol, how exactly we can decide on whether this protocol works correctly or not. We can do that using the measure of fidelity. Fidelity is the square of the inner product between the input and the output state, and it takes values from 0 to 1. And fidelity is equal to 1 if and only if the two states are identical. So what we expect is perfect teleportation should give us fidelity equal to 1. And that is the plot of the fidelity for different entangled states as resources. And as we can see, for x equal to 0, we end up with this separable state, and we have fidelity equal to 1/2. And for this Bell state that we already seen, we end up fidelity equal to 1, meaning that the teleportation was successful. And in that sense, we can call that a maximally entangled state. And all the rest of the states, all those states for parameters from 0 to 1/2 are also entangled states, but not as much entangled. There's a lot of things that we can say about how to quantify entanglement, but in this case, I guess it's kind of simple to see that using that characterization of entanglement, we can see that the more entanglement we have, the better the teleportation performs. And for maximally entangled states, we actually achieve the perfect teleportation. And with that, I would like to conclude this lecture. And next time, we will try to see what happening with, if we introduce noise, we'll see how we can expand the protocol of teleportation in something that is called entanglement swapping, which help us distribute entanglement. And that will be helpful to discuss about how we can distribute entanglement in large-scale scenarios like quantum networks. And I give you again certain books in case you want to read further on those topics. Again, you can find all those slides on my personal webpage, and you can always reach out to me on my email. And I'm happy to take any questions if there are ones. I already see a question on the comments. Could you comment on deterministic and non-deterministic quantum teleportation? So at this point, since we are only working with pure states, the teleportation can work as long as Alice knows the results and broadcast them to Bob. The non-deterministic part is happening based on the fact that Alice doesn't know exactly what results she will get. This is, in that sense, non-deterministic. There are cases where we can also assume that there are different ways to discuss about deterministic and non-deterministic. For example, the creation of an entangled state can be deterministic and non-deterministic, depending on the platform. I haven't talked at all about continuous variable teleportation. You might have seen comments on the deterministic teleportation on the continuous variables because they're the way that entangled states are created are in a deterministic way rather than discrete variables. I skipped the part of how easy it is to practically end up with those entangled states. I see another question. CNOT cannot be implemented deterministically or optically. How does it affect teleportation? It affects teleportation in the sense that we cannot have a single quantum state and just end up teleporting it. What Alice and Bob have to do is to have an ensemble of similar states at Alice's side and keep doing that protocol until the point where everything will work correctly and the teleportation will be successful. So yeah, there is no way to, and unless we're super lucky, to have a single quantum state and teleport it with one shot from Alice to Bob. Are there any more questions? Anyone? All right, that's great. So if there are no more questions, I will see you again next week for the third and last lecture. Thank you all very much. Oh, I have a question.